And welcome to this video lesson on inverse functions. This is part 2 of a 2-part lesson on inverses, and this particular video is going to focus on graphs of inverses. And it's also going to include the practice set, because while graphs of inverses are an important concept to have, it can be very useful to understand it. It's also not like a really broad topic with like lots and lots of problems. So instead of making a separate practice set video, it is embedded in this lesson. Please like this video if you find it helpful, subscribe to the channel for more math help, and drop a comment or question below. Please also check out the many other videos and playlists on the channel, and I will be sure to link some of those at the end. Now, what have we already covered in our study of inverses? Well, key idea is that inverse functions have their domains and ranges switched. So in other words, the set of possible x values and the set of possible y values get sort of flip-flopped, and we end up with these functions that undo each other. So if you take something from one domain, it outputs something in the range. The inverse will take that output from the range and bump you back to the original number that was in the domain. So as an illustration of this, let's say you have a set of numbers. We'll call this set A, and then this other set of numbers over here, set B. And for our original function, we'll just call it function f. F will pull something from set A, meaning the domain. Okay, so this would be our input. It'll pull something from there, and it will output something in set B. And this would be its range. So this set of numbers over here would be its range. The inverse goes in the other direction. So our inverse function will pull something over here from set B, which would be its domain, and will output something over in set A, which would become its range. And so you've got this like back and forth going on. If you wanted to think of it as a specific example, maybe the number 2 goes into the function and we get a 3 out. Well, the inverse would take the 3 and output back the 2. Now, if you like to go over that in more detail, or you're realizing that this is not a concept that you actually have studied with inverses before we go too far into the graphs, please go and check out part 1. I am going to go link that up in the corner up there. So click on that, get that video lesson, and then come back and you'll have a little bit more of the same footing for studying the graphs. So that leads us to this question: what impact does this have on graphs? So for our first example, we're going to look at just a set of ordered pairs, okay? And this right here, that's the inverse function. Okay, that's how I have to do that in Excel. So it's a little caret. So we have the function, and then we have the inverse of the function. And what I'm going to do here is start by plotting this set of points, but we'll kind of go in phases here. So using my red pen, my function f has the point -3, -1. So I'm going to come over here to -3 and -1 and put a dot right there for that. Now, when we go and find the inverse, okay, inverse means we're switching your domain and your range, or again, if you look at the other video lesson, you know that we essentially switch the x and the y. So for my inverse, instead of -3, 1, I'm going to have -1, -3, which is going to put that right there. So I'm going to do the original set of ordered pairs in red, and I will do the inverse set of ordered pairs in green. And so we've got, say, the point -2, 5, which would put me right there. And then that would become the point 5, -2. So 1, 2, 3, 4, 5, -2. And what I tell my students when they're doing this is look for a pattern. Now, this set of ordered pairs is essentially random. I did make sure it was a function, but other than that, like I just picked some numbers. So you shouldn't see a pattern necessarily in like the red dots, but you should see a pattern between the red dots and the green dots. And you can actually start to see one already forming here. Hopefully you see one forming. Next ordered pair is -1, -6. So that puts me down here. And when I switch that, that'll become -6, -1, which will put that there. Now that might have messed up whatever pattern you thought you were seeing, but we're just going to keep on with it. The next point is the point 0, 1. And when we switch that, it becomes the point 1, 0. Okay, that looks like it more fits the original pattern. Next point is the point 1, 2. And that, when we switch it, becomes the point 2, 1. Which puts it right there. So at that point, I think we can definitely see we've got something going on there. Next up is the point 2, -3. So over 2, down 3. And switching that becomes the point -3, 2. So 3, up 2, that puts it right here. And then last but not least, we have the point 3, 1, 2, 3, 4, which is up there, and the point 4, 3, which would be 1, 2, 3, 4, 1, 2, 3. Okay, and as you look at like where these dots are, I think for at least me and most of my students, they look at that and definitely see that there is a pattern. So what I'm going to do in this video is what I told my students to do, which is I gave them about 10 minutes to plot the points and consider what kind of pattern they thought they were looking at. So pause the video. We got all the points plotted. Give yourself some time to look at these ordered pairs and generalize what you think the pattern is. Okay, hopefully you did do that. And now my students will often come up with a variety of things. Some will see like a rotation. Some will see like reflections. It can be difficult to kind of nail down what you think you're seeing. Now, what I had a student do the last time I did this was he actually on his page did in very, very faint pencil lines, he connected the points that went together. And I thought that was a brilliant idea. In fact, I think I'm going to record a short where like I share that like little idea that he had, and when you're asked to like look for a pattern. So what I'm going to do is use the highlighter, and I'm going to use the yellow highlighter to kind of mimic what he did. So the point -3, 1, and the point -3, -1, and the point -1, -3 is these two. Then we have -2, 5, and 5, -2. So that connects these two. -1, -6. And -6, -1 are those two. 1, 0, and 0, 1 are those two. 1, 2, and 2, 1 are right there. Okay, and so like those all seem to be like on a line together, so they got like covered. We have 2, -3, and -3, 2, which is these two, and then 3, 4, and 4, 3, which is these two. And when you connect them, Like, I really thought it was pretty brilliant, because when you connect them, the way that they're all tilted gives you an idea of where the line of symmetry is, because it would be at the center of all of these lines. So if you're looking at like the center, like where is the center of all of these lines, it's like right there. So that one you can actually see it really well. This one, I don't know if we can see it really well. It's like right there. But when you do that, I think we might be right there. You can see like, oh, the center of all of those lines is where the line of symmetry is. And would be awesome is if I did that better. If I could do that without drifting. There we go. That's better. Okay, kind of like cutting through all of those points. And you see that that is the line y equals x. It goes through 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3, and so forth. And that is the line y equals x. So I really thought that was a creative way that he was probably just trying to keep track of, this is the original point and this is the point that I get when I switch the x's and the y's. But by drawing those lines, he gave himself an extra visual tool for finding where the line of symmetry is. So when you're dealing with the ordered pairs and you're looking at these inverses where you're switching the x's and the y's, the graphs are going to be symmetrical, and the line of symmetry is the line y equals x. Now, just to drive home why that makes sense, okay? Suppose we had the point, we'll say -8, -8. And so I go to -8 and I go to -8. And it's going to be right there on the line of symmetry, on the line y equals x, because indeed y and x are equal. So when I switch them, I also get the point -8, -8. So this is like yx, but they're still the same. And so when you have x and y being exactly the same, then it's going to be on the line of symmetry, so there's no reflection visible. It's like it flips or turns onto itself. And this would be true if I had the point, say 6, 6, 6, 6, which would be up there. Okay, the point 6, 6 would reflect onto itself. And again, it's on the line y equals x. So key idea right here, key idea is that inverses are symmetrical over the line y equals x. They're not symmetrical over the x-axis or the y-axis. They're symmetrical over the line y equals x. So how does this look with linear functions? So we're going to look at the linear function there. This is example 2. And so this gets into the previous lesson. If you are finding the inverse, you might go ahead and swap out the f of x for the y. Then we do this switch of the x and the y. That is the switching of the domain and the range, switching the input, the output. Now we'll go ahead and solve for y. So we'll subtract 4 from both sides. So x minus 4 is equal to 1/2 y. And then we'll multiply both sides by 2. And that will give us 2x minus 8 is equal to y. That's the new inverse function. So going back to that f of x notation, we get the inverse is 2x minus 8. I don't want to jump to say, oh, it's 2x minus 4, like because I added 4, so now I'll subtract 4. Doesn't quite work that way. So we've got that. So how does this look like in terms of, or what does this look like in terms of a function? So what I wanted to do here was actually approach this a couple different ways. So you could use the shortcut. Okay, so we'll kind of look at the shortcut here. We'll do this one in orange. So the y-intercept is 4 and the slope is 1/2. So I'll go up 1 and right 2. And technically that's all you need to graph the line. But because we're really looking for some symmetry here, what I'm going to do is give myself more of those points. Okay, more of those points, just so I can get a more accurate graph. So so there we go. So this is gonna go like so, right across like that. And then we'll use green for this one. And this has a y-intercept at -8. And the slope is, let's get that back. There we go. And the slope is 2 or 2/1. So I'm going to go up 2 and right 1. So up 2, right 1, up 2, right 1. Okay, like that. Do up 2, right 1, up 2, right 1. And then we'll go down to left 1 and do our best job connecting those. Now, if I go and draw in the line of symmetry there, I think looking at that just the way it is, it's a little bit hard like to see the symmetry. It's much easier to see the symmetry if you go ahead and draw in that line y equals x. There it is. Sorry, drifted a little bit. And now you can see it better. But what is actually even better to do is take a look at some ordered pairs. So for example, on my original function, I see the point 0, 4. Okay, there's the point 0, 4. And on the inverse, I actually do see the point 4, 0. So there it is, 4, 0 and 0, 4. And if I want to do that thing where I just connect them to see the symmetry, oh, like there they are. Now I might pick another point. So maybe if I look at, say, if x is equal to 2, okay, so I have 1/2 times 2 plus 4. Well, 1/2 of 2 is 1 plus 4 is 5. So when x is equal to 2, y is equal to 5, we should be able to find that. There it is, right there, the 0.25. If I come over here to my other function and I plug in x is equal to 5, 2 times 5 is 10, and 10 minus 8 is 2. So when x is 5, y is 2. Like you can see it come out in the function, like the input output, and we can see that over here. So when x is 5, y is 2, and we see those okay, and let's try that one more time. We see those sister points. And then just for fun, let's pick something down here. So here I seem to have, we'll just do -6, 1. Okay, so let's just double check that. Looking at when x is -6, that would be -3. Half of -6 is -3, and -3 plus 4 is 1. So I end up with the point -6, 1, and that's this point right there, which means on my inverse, if I plug in a 1 for x, so I do 2 times 1 minus 8, 2 minus 8 is -6. So indeed, I do get 1, -6, which should be right there, and it is. And when I connect those, I see, once again, I see that symmetry over that line. So this, I think, brings it completely full circle. We see the process of finding the inverse, the switching of the x and the y's. We see the symmetry on the graph, and we can see that idea of doing and undoing. If I plugged in a -6 into the original, I got a 1 out. When I took a 1 into the inverse, I got a -6 out. We see the switching of the ordered pairs. We see the symmetry on the graph. And it, of course, could be any and all of the points in between. Like, it doesn't have to be those 3 points. So you can really see the doing and undoing, the ordered pairs, and the symmetry on the graph. So we're seeing all aspects of it. Now, let's quickly look at graphs with domain restrictions. So this is the graph of the square root of x plus 1. So this is a square root graph that has been shifted to the left 1 unit. All right, so kind of reviewing that. So this is a square root graph that goes left 1 unit. Now, what I'm going to do here is actually plot the ordered pairs so we can get a good look at that. So we have the point -1, 0, which is right there. The point 0, 1. And you could test all of these out. So if I plug in -1, that's the square root of -1 plus 1, which is the square root of 0 or 0. If I plug in a 0, that's the square root of 0 plus 1, or the square root of 1, which is 1. If I plug in a 3, that's the square root of 3 plus 1, which is 4. So the square root of 4 is 2, which is where we get the point 32. And we could do the same thing with the 8. And obviously, like, 8 plus 1 is 9, and the square root of 9 is 3, so we get the point 83. So I obviously picked those in a very intentional way to get good numbers out. So we have the point 32, and then the point 83, and that gives us that shape of the square root graph going up in that direction. So the inverse, then, we could find by just switching the ordered pairs. So switching up my colors. So we could have 0, -1. So that'll be right here. We have 1, 0, which puts us right there. The point 2, 3, which puts me right there. And the point 3, 8, which puts me up there. And what you see there is not the entire parabola, but you see just the half of the parabola. So going to our issues of domain and range, if I look at this function, the domain of that function is x is greater than or equal to -1. How do I know that? Well, because it starts at -1 and it goes to the right, so my x values are greater than or equal to -1. And you can also see that by plugging in, like if I plug in a -1, -1 plus 1 is 0, the square root of 0 is 0. But the moment I go to like a -2 or even a -1.1, whatever that is, plus 1 will give me a negative, and it will not be a real number. The range for that is y is greater than or equal to 0, because the smallest number for y I can get out of this is a 0. I can't take a square root and get like a negative number out of it. So that's my domain and range. So what that means is, for my inverse, okay, the domain and range end up swapped. So we have x and y. The domain will be the same as the range here. So y was greater than or equal to 0. Then I end up with x is greater than or equal to 0. And if my range is coming from your domain, then my range would be y is greater than or equal to -1. Well, check out the graph. Okay, right here, here's my x's. The x's begin at x is equal to 0, and they go to the right. And my y's are beginning here at the -1, and they are going up. How does that play doing like the math out? Okay, so we have y is equal to the square root of x plus 1. Then we switch that. We switch the x and the y's. Then we square both sides to get rid of the square root. And then we subtract the 1 from both sides. And we end up with y inverse is a parabola that is going down 1 because the subtraction is outside the squaring, but it's not the whole parabola. Like the whole parabola would be like that and the other side of it. Sorry for how messy that is, but we don't want the whole parabola. We have that restriction on the domain. It's got to not be both sides of it. It's only the reflection over the line y equals x of the part of it that was incorporated in the square root function. And so if I draw like my line of symmetry, okay, there it is. And you can see that symmetrical part, and you can see that where the two graphs cross is on the line y equals x. So that domain restriction like comes over into the inverse. All right, so this is the practice set. Go ahead, pause the video to work these problems on your own, and then come back and check your work. All right, so we're just gonna work these right on the screen. Hopefully you did pause the video. If you didn't, please pause the video. Like, don't just barrel through and get solutions. So the first one is just look at the graph below of f of x is equal to x minus 4 all squared. That's the one that's in black. And what you want to notice about that is that this is a parabola. We know it's a parabola because it's squared, and we know that it goes right 4 because of the minus 4. And so there it is. That's the one that's in black. And we are asked for the inverse, and we're given 3 options: the blue, the green, or the red. Now, what is tricky about this is the blue, the green, and the red are all reflections of the graph, but they're not necessarily reflections over the right line. The blue one is a reflection over the y-axis. So if I use the y-axis as my mirror, then you can see the mirrored points. Okay, so we got like this point mirrored here, and this point is mirrored here, and the vertex is mirrored. Okay, and you can see that when you connect the corresponding points, like the lines are all horizontal, so the mirror line would be in the middle. Well, that is a reflection, but it's a reflection over the wrong line. It's not a reflection over the line y equals x, so not the blue one. The red one is also a reflection, but that is a reflection over the x-axis, so it's a reflection over that axis there. So if I were to like kind of connect my mirrored points, the vertex is like reflected onto itself, but you've got like your mirror points are stacked up that way. So that eliminates the red one. Yes, it is a reflection, but no, it is not a reflection over the correct axis. So that brings us to the green one. So it better be the green one, but man, that looks weird. So what I would recommend doing is going and drawing in the mirror line. So the line that should be acting as the mirror. Really? It does not want me to draw this. Okay. Let's try doing it this way. It should be the line y equals x. There we go. Yeah, like the line y equals x. So now let's see if we have the right kind of mirroring, whether it is easy to see or not easy to see. Like, let's see if what we're getting is actually like a mirror image. So right here, I can look at the vertex of the parabola, and there's the other vertex, okay? Where the two coordinates are equal, where they're intersecting, or at least where they're intersecting some of the time is on the line. But look at this point of intersection right there. it's got its mirror intersection on the other side. That intersection and that intersection are on the line. You got a mirror point there. If I look at where they're going off the grid, there's a mirror point there. And now you can see, oh, those lines look the same. I tell you what, my student did was brilliant. Going to be using that forever in how I illustrate this. And you can see that those lines, the center point of those lines is the line y equals x. So the correct answer to that would be the green function. Okay, question 2 is the inverse of f of x in number 1 also a function? So this goes back to the definition of function, and for a function, each x can correspond to only one y value. So if we look at the green function or green graph there, that is actually not a function. Because let's just say for x is equal to 4, there are 2 y values that go with that. So we have x is 4, it looks like y is 2, and again, x is 4, y is 6, I believe. Yeah. So let me see, 2, -2, 6. Yeah, okay, that makes sense. And so there are 2 y values for like a given x value, and there's of course more than that. Those are just the ones that we could see. But here, when x is 1, we've got y is 3, and when x is 1, y is also 5. Okay, and that actually happens infinite number of times, some of them with nice numbers, some of them with not nice numbers, but it is not a function. So that is a case where the inverse of the function is not itself a function. Not unless you put some kind of restriction on the original black parabola and say, hey, I only want the left half of this, or I only want the right half of this, then you would be okay, because then you would not be reflecting the whole thing. But we do get a little bit lazy about that. So you heard me do it a moment ago where I said inverse function, and I just kind of blurted out the word function when I knew that the inverse was not a function. So there you have it. All right, and the last one, sketch the inverse of the function shown. So the actual function there, if I turn the highlighter on, and like the actual function is this, okay? It's the connected piece of that. It looks like that. What I did in order to make this easier for you, or to give you a hint, was on the function, I put some dots. I put some dots on there so you could have something to work with. So there's 2 ways you could do this. One way that you could sketch the inverse is draw that symmetry line, which I did not do a great job of, but in theory, if you had, say, graph paper in front of you, okay, and you had a ruler or something, you could do that much nicer. And then you could eyeball the symmetry, okay? You could just kind of eyeball it like that. I find that a lot of students do not eyeball it really well. So it's good to have an idea of where that inverse should be, but maybe don't eyeball it. So what you should do if you need to generate any kind of nice graph is find some points to anchor your graph. Now, what I did to try to make this a little bit easier for you is I gave you some points to work with. So this point right here is the point 0, 1. So you can go ahead and you know that 1, 0 will be on it. This looks like the point 1, 2. So I'm going to go ahead and plot the point 2, 1. The next point. Oh, wait a minute. Sorry. That was 1, 0, 2, 1. Okay. No, that was right. Except that looks like the point, 2, 4 right there. So that'll end up being the point 4, 2. So that'll put that there. And we have the point 3, 8, which would become the point 8, 1, 2, 3 like that. And then there's this point over here, which is a little bit harder. This looks like maybe -1, 1/2. So that would be like 1/2, -1, maybe right there. And then now you've got something a little bit better than just eyeballing it. You've actually got some points to look at. Now, got a little messier there than I wanted to be. If you look at this, this does not appear to be touching the x-axis, which means on this side, you do not want to touch the y-axis. That can be kind of drifted across that. And you should see that symmetry. And again, you could connect the points with that like diagonal line, gotta find the center of it. So there you have it. You could also do this with like a ruler or count the symmetry. So you could do something like this and say, okay, this is 1, 2, like 3 blocks away like from the line. So it's 1, 2, 3 blocks away on the other side. This is 1 block away. So it'll be 1 block away, like that kind of way of counting. It's a little bit more with some geometry. So anyway, your final graph should look like that, something close to that. It should not cross the y-axis, so you can kind of take a look if you have almost the right thing, but it kind of drifted across the y-axis, like mine did that. I had to erase it, so you can kind of make that that correction. All right, so that's what we got for practice problems. Please don't forget to like and subscribe for more math help. And if you found this helpful, please give me that like. It only takes a second. Drop a comment or a question below to engage, and check out the many other videos and playlists on the channel. I will go ahead and link over to a playlist that you can check out at the bottom of this video, and I hope to see you in a future video.